Log on, tune in, find out. Another good idea from Cambridge.
Here's Paul Williams to talk about the importance of numerical time-stepping errors.
Thanks, John. Good afternoon, everyone. Yes, so time-stepping errors, which I think it's fair to say are often assumed to be negligible when quantitative assessments of uncertainty in climate predictions are being done. So there are many people who will spend a lot of time doing ensembles with perturbed parameters, but I don't think anyone's done an ensemble yet with perturbed time stepping to try and quantify uncertainty due to time stepping. And that would be defensible if the time step being used in the models was sufficiently short that numerical convergence had been achieved. But of course the pressure on models is to use as long a time step as possible, so you can do long integrations, have lots of ensemble members, include lots of complicated physics and other bits of the Earth system. And so I'll show you some evidence. I mean, I've done some digging around in the literature, and it's not difficult to find evidence that these simulations are not converged as the time step is decreased. So I think there is evidence that time stepping errors need to be considered. And in the second part of my talk, I'll outline a sort of possible avenue for progress with time stepping schemes. And in particular, I'll describe a modification I've proposed to the time stepping scheme that is used in most weather and climate models, a very simple modification that's easy to implement, doesn't increase the computational expense at all, and increases the accuracy of simulations. Right, so I'm aware that this audience is perhaps unusually broad, so just to put what I'm about to say in some sort of perspective, I'm going to break down sources of uncertainty in simulations of, well, climates really for this audience, but also for weather. Of course, the initial conditions are uncertain, especially important, of course, for numerical weather prediction, but also for initialized seasonal and even decadal climate predictions. Not difficult to estimate that uncertainty by doing an initial condition ensemble, and those are of course widely done. There's also uncertainty from the boundary conditions and the external forcing, greenhouse gas forcing, for example, very important, and again not difficult to run an ensemble of climate integrations with different greenhouse gas forcing scenarios and estimate that contribution to uncertainty. And then of course there's model error, or simulator error as perhaps I should call it, and that's what this talk is about, of course. And that can be broken down, I think, into dynamical assumptions. If your model imposes or assumes hydrostatic balance in the vertical coordinates, then that is an assumption that breaks down in a certain limit on small time scales. Certainly the first computational weather predictions were done assuming geostrophic balance in the horizontal coordinate, and that contributed to errors in those forecasts. And then of course there are parameterizations with parameters, the values of which are not very strongly constrained by theory or observations. So there's uncertainty in those parameters too. And again, that can be estimated by running ensembles with different parameter values. But then of course there are numerical errors too in models. Often neglected, I think. Many people would associate parametric error with model error, but model error is not just errors in the parameters, but also in the numerical schemes that are used to integrate the continuous differential equations. And this talk, of course, is about those numerical approximations, which come both from discretization in space and in time. And I'm talking today about the time discretization. And just for those who are unfamiliar with this, of course, time in the real world is continuous. Well, time that's a bit philosophical. Time in the time continuous partial differential equations, time is continuous. Whether time in the real world is continuous is beyond the scope of this talk. But of course, in any computational model, because of finite computational resources, we have to divide time up into these discrete chunks of length delta t. So you can't get from one time level to the next continuously. You just jump discretely from one time level to the next. There's no unique best way, or there's no exact way to do that. All there are is a set of approximate ways of doing that, some better than others, all with different errors. And because of those errors, discrete time stepping is in principle going to make a contribution to model error, and hence to uncertainty in simulations of weather and climate. Right, this is one of my favourite tables, if it's sort of acceptable to admit to having a favourite table. I know you can't see it from the back, and that's not important. It's just a table, each row of which gives some of the properties of various time-stepping schemes. All your favourite time-stepping schemes are here. The leapfrog, the runner cutter, and Adams-Bashforth schemes. So, you know, I mean, I think in principle there's an infinite number of different time-stepping schemes, and this table just lists a few of the common ones. And I'll show you evidence that which particular time-stepping scheme you choose from this list to implement in your model affects the simulated climate surprisingly strongly. And not only that, but for a given time-stepping scheme, the length of the time step that you use also affects the simulated climate. That's the first part of the talk. And then into the second part, I mean, you might think that picking a scheme from this list is a little bit like picking a parameter value, picking a value for the cloud entrainment rate, for example, which is not well known. But actually, we know from simple numerical analysis some of the properties of these schemes. This list actually of time-stepping schemes is ordered from least accurate at the top to most accurate at the bottom. So you might think we should be using a time-stepping scheme near the bottom of this list. But the time-stepping scheme that's used in most climate and weather prediction models, with a few exceptions, is this one. It's the leapfrog with an Asselan filter. I'll say more about that shortly. But you'll notice it's right near the top of the list. It's not a very accurate time-stepping scheme. And the reason we don't use the more accurate, you know, fourth order schemes is that, and I think you can see that actually that the further you go down this list, the more complicated these formulae get. And particular, I mean, you can almost draw a triangle here. I think these formulae at the end, you know, contain lots of function evaluations. They're very demanding computationally relative to the schemes at the top of the table. The runtime memory requirements are much higher. So I think we're stuck with this simple scheme at the top, and in the second part of my talk I'm going to outline a method for improving this well-used time-stepping scheme, and in fact increasing its amplitude accuracy from first order, as it is at the moment, to third order. So it's going to match the high amplitude accuracy of these Runge-Kutta and Adams-Bashforth schemes towards the bottom of the table. Right, so a bit more motivation first. I've stolen this slide, I think, from Tim. I'm going to explore time-stepping errors in the Lorentz attractor. You all know about this from Tim's talk. Here are the equations. This is a very useful toy model for examining many of the contributions to uncertainty in climate prediction. For example, you can explore initial condition uncertainty by launching an ensemble of runs in a sphere here and watching how they diverge apart in time. You can explore the impact of forcing uncertainty by adding forcing terms to the right-hand sides of these equations and looking at how the climate of the Lorentz attractor changes. Tim talked about that. You can explore parametric uncertainty by varying the values of these parameters, sigma, rho, and beta. In fact, Tim, in his 2001 paper, showed that if you try to parameterize what appears to be the least important mode of variability in this system deterministically, then that is doomed to failure, and only a stochastic parameterization can recover the structure of the attractor. But what I'm going to talk about today is time stepping errors and the impact of different time steps and time stepping schemes on the attractor itself. Right, so here's an integration of those equations I did using a simple first order forward time stepping scheme, first order Adams-Bashforth scheme, or the Euler scheme, using this time step. And this is just the x and the z components, and it looks like Tim's picture. So that's all very well, but let's suppose that, you know, we work at a climate modelling centre and the director tells us our model's running too slowly. Can we do anything to speed up our model? And of course the obvious thing to do is to increase the length of the time step, and you might want to do that so that you can integrate out further in time for the same computational expense, 2 centuries perhaps rather than just 1 century. You might want to have 100 members in your ensemble rather than just 50. You might want to add more complicated physics and chemistry and plug in new bits of the Earth system. So you increase the time step to try and make the model run more quickly. So if you increase it by a factor of 10, which is perhaps quite a large increase, this is the structure of the attractor that you get. Now at first sight it doesn't look too bad. It's got the 2 wings, certainly, so the structure looks the same. The space spanned in the x and z coordinates is roughly the same. So perhaps it doesn't look too bad. However, if you look a bit more closely, and in fact you don't have to look that closely, you start to see differences between the 2 attractors on the left and the right. For example, I mean, there are at the centre of the 2 wings of the attractor, this is fully converged, by the way. If I decrease the time step further, this attractor doesn't change noticeably. So the fully converged exact attractor, if you like, doesn't really explore these gaps in the middle of the wings, and you see that, I think, here as well. But that's clearly not the case when you increase the time step. The centres of the 2 wings are being explored much more than they should be. And in fact, close to x equals 0, the space is not being explored enough, it turns out, compared to the plot on the left. I'll show you that in the next slide. So I just make the basic point here that the structure of the climate of this dynamical system is sensitive not only to the parameter values and the forcing, but also to the numerics. So let's look at what you can think of as being probability density functions for, in this case, the x component of this system. I've just done very, very long integrations here and binned the value of x from a very long integration. And here's what you get with the short time step. You see the 3 peaks in x, which correspond, x is on the x-axis here, conveniently. You see a peak corresponding to this bunch of trajectories, and a peak near the middle, and another peak at positive x. That's what these 3 peaks are. But for the attractor on the right, the PDF looks structurally very different. What used to be a trimodal structure has become a bimodal structure, for example. And what's happened is that these 2 new peaks here, which were not present in the original attractor, correspond to the centres of the 2 wings. Now, and there's another bias, which is that the red curve is not high enough near x equals 0. So there are substantial biases in the red attractor compared to the black one, which we can take to be exact, that are there because the time step is too large. And we can understand the origins of these biases as well. There's linear damping, for example, in x, y, and z in these equations, and so all other things being equal, of course, you know, we should just be seeing exponential decay in x, y, and z with time towards x equals 0. But with this time stepping scheme, if you try and get away with using a large time step, I mean, the time stepping scheme takes dx by dt at the start of a time interval and just propagates it forward, extrapolates it forward in time. And by doing that, it's overestimating the magnitude of dx by dt. So while the attractor should be slowing down as it gets close to x equals 0, it's actually going far too quickly, and as a consequence, it's not spending enough time near x equals 0. So, I mean, these trajectories in the black case are starting to, as they cross from one wing to the other, starting to move parallel to the z-axis in this plot, but they're not doing that in the red case. They're not slowing down, and dx by dt is not slowing down. The trajectories are moving far too quickly over to the opposite attractor, and as a consequence, they're not going to the outskirts of the attractor, but they're actually ending up near the center, and that's responsible for this bias. So, I mean, clearly there's a bias here due to using too long a time step, and we can understand in terms of the, the algorithm for this time stepping scheme, the origins of those biases. There's no change to the mean value of x in this case, and that's because of a symmetry in the equations, which is present for x and y, but not for z. So here's the corresponding frequency histograms for the z component, both for the converged exact attractor and for the larger time step attractor. And in this case, because that symmetry that was there for x is now absent, there is in fact a change to the mean value of z. So I just put this up as an example of changes to the climate of the Lorentz attractor due not to poorly known physical parameter values or unknown forcing, but due to the numerical time stepping scheme. A few examples now in sort of proper atmosphere and ocean models. I mean, these authors looked in ECAM6, which is a well-known atmospheric general circulation model. In this case, a single column model version of ECAM6, so just a single vertical column being integrated here. And they've imposed a 2-degree warming at the bottom boundary in this model and looked at the change in the cloud radiative forcing. I mean, this 2-degree change changes the low cloud structures. And because low-level clouds cause a net cooling, there's a change which is documented here as a function of the time step, a change to the cloud radiative forcing for low clouds in watts per meter squared. And I don't know whether you think convergence has been achieved here. Certainly the path towards convergence is not monotonic. If you use a time step of 720 seconds, you get a change of -3 watts per meter squared. It goes up in magnitude to 9 and then it starts to come down again. So there's something very bizarre going on here. Of course, the time steps that are used in practice are the long one here, or in fact even longer ones than that.
What's the advection scheme that you used in the simulator?
Well, it's just a single column, so I don't quite know what they've done, but there's no advection, I think, coming in. There must be, yeah.
Ideally, you would develop your parameterization schemes so that they don't have a dependence on the time step.
But that's not done.
That's not done. So this isn't necessarily a numerical error. It could be a parameterization.
Absolutely. In fact, there's probably almost certainly a complicated interaction between the time stepping errors and the parameterization errors, as these authors conclude here. Complex interactions between physical parameterizations and numerical artifacts. All sorts of other examples. Matt, you talked about the double intertropical convergence zone in your talk. This is the zonal mean precipitation in another atmospheric general circulation model, plotted as a function of latitude for 2 different time steps. I don't really want to have time to talk about which of these 2 simulations is the better, but I'll just make the broader point that the zonal mean precipitation pattern is strongly dependent upon the time step. Even a change in the time step by a factor of 2/3 is enough to radically change the zonal mean precipitation structure in this model. So again, an example of a lack of convergence. As you try and make the time step go to 0, the basic climate changes significantly.
Is this any?
Oh, sorry.
Well, a quick question. You just said you didn't want to talk about which one was better, but isn't it always better to have a smaller time step, or not necessarily?
Ah, right. Sorry, I just meant which of these two structures match the observations more closely. Of course, it's always...
It's an aquaplanet.
Right, okay, well, yeah, okay. I just make the basic point that, you know, this double structure here, the double ITCZ, goes away when you change the time step a bit. So there's a lack of convergence. You're right, it's an aquaplanet, so there aren't any observations of an aquaplanet with which we can compare it. But certainly it's always better to have a smaller time step. Now I have to take a quick audience survey before I talk about this slide. Are there any MICOM developers in the room? And this is not going out on the internet or anything silly, is it? So I can... MICOM is the Miami Isopycnal Coordinate Ocean Model, very well respected ocean model. And there's just a diagnostic here of the ocean thermohaline circulation, one of the most climatically important features. I don't have time, I think, to say as much about this as I would like, but what's plotted here is, this is an isopycnal coordinate model, so you have the less dense isopycnals and going deeper into the ocean down to the most dense isopycnals, and then there's latitude from 60 south through the equator to 60 north. And what's plotted here are the diapycnal volume fluxes, which are approximately the sort of vertical volume fluxes. And what you see, blue means a flux to more dense water, red means a flux to less dense water. And what you see here are these blue fluxes. This is one Sverdrup, which is 1 million meters cubed per second of transformation in the water flux. These blue bars are the downward branch of the thermohaline circulation, dense water, deep water formation at high northern latitudes, and the distributed red bars throughout the three-dimensional ocean are a gradual return flux back up to the surface of those dense waters. So that's the thermohaline circulation, and it looks all right, doesn't it? Except that it's not as good as it looks. And in particular, if you take a given isopycnal layer, this is derived, by the way, from a 3,000-year integration, so the deep ocean is in equilibrium. If you take a given isopycnal layer and integrate all the volume fluxes into and out of it, you ought to get zero, because the thickness of the layer is constant in time. So for every meter cube that goes in somewhere, there must be a meter cube coming out somewhere else. However, if you actually integrate those fluxes over the boundaries of the layer, you get something that's not zero. It's between 5 and 10 Sverdrups. That's what's shown here. So how can that be? These layers are observed not to be thickening or becoming less thick with time, and yet there's certainly a divergence to this field which ought to be changing the thicknesses of isopycnal layers with time. Of course, what's happening is that these physical fluxes are being compensated by numerical fluxes, which are as large in the North Atlantic deep water formation regions as the physical fluxes. So here's the integration, and it exactly balances the physical fluxes, and everything sums to zero. So this is just an example of compensating errors. I mean, this plot on the right should be zero. I mean, these fluxes should be zero, and these fluxes should be higher than they are. But as it is, when you take the sum, the overall thermohaline circulation looks reasonable. This is a good model. It has a good thermohaline circulation, but it has it because of a compensation between these errors, which are too big, and these fluxes here, which are too small. So it's the classic compensation of errors mechanism. Certainly, as the time step, and what I haven't said yet is that these numerical diapycnal volume fluxes are coming from the time stepping scheme. So the time stepping scheme in this model is generating as much North Atlantic deep water as the physical mechanisms in the model, the high latitude surface buoyancy loss. I find that pretty astonishing, and I wouldn't want to be using this model to look at the fate of the thermohaline circulation in a changing climate or anything, when roughly half of the circulation is coming from the numerics rather than the physics. Anyway, that's how it is. There are plenty of other examples in various models of a lack of convergence as the time step goes to zero, or as different time stepping schemes are implemented. In this particular model, the two different time stepping schemes give different precipitation patterns. For example, a lot more precip in the western tropical Pacific with the leapfrog than with the Matsuno. So the authors conclude that simulations are sensitive not only to the physical parameterizations but also to the numerics. More evidence here. This is the zonal mean temperature error in the CAM, community atmosphere model. Error relative to era 40, so to what we think the atmosphere actually looks like. The zonal mean temperature plotted as a function of latitude on the x-axis and pressure on the y-axis. And you see these large biases of 10 degrees or more in the temperature of the polar jet. And those biases are a function of the time stepping scheme. If you switch from leapfrog to Adams-Bashforth but keep everything else the same, including the length of the time step, these biases are halved, well, not quite halved, but certainly they're changed. And so I just put this quote up from these authors, that in weather and climate prediction, when thinking in terms of model predictability, there's a tendency to associate model error with the physical parameterizations. And these authors give evidence that time truncation error can also be a substantial part of the total forecast error. So what can we do about this? This is part 2 of my talk. This is the scheme that is used in most weather and climate prediction models, with few exceptions. It's the leapfrog scheme with a time filter applied to stabilize it. It's very widely used in atmosphere, ocean models, coupled climate models. You can spot your favorite model from this list. We talked about metrics of climate models. Here's a metric of papers, the number of citations it's received, mostly in journals of atmospheric science, but also oceanography and fluid dynamics. But people have said for a while that the Robert-Asselin filter, it's been immensely popular. It's been used widely for 20 years. In fact, that was written 20 years ago, so it's been used widely for 40 years now. However, it's not the last word, and other authors have also agreed that replacing this time filter could be a feasible way to improve the fidelity of the ability of climate models. So here's how the leapfrog scheme works. As you all know, you use a leapfrog scheme to calculate the state at the future time level from the 2 previous time levels. And then, if you do nothing else, the simulation will exhibit the famous time stepping instability, where the even and odd time steps decouple. So what is done in practice is that this Robert-Asselin filter is used to nudge the middle state vector up towards the midpoint of the 2 outer state vectors, and that stops the even and odd time steps from splitting apart. However, it also reduces the accuracy of the integrations. And this is only a first order scheme. So in a paper last year, and in fact this 2011 is a reference to a paper I've been working on whilst I've been here at the Institute, which is now available as a Newton Institute preprint. It's a submitted paper to Monthly Weather Review. I've suggested an improvement to this time stepping scheme, which starts out the same way as the one on the left. Remember, this is very widely used in contemporary models. You do a leapfrog step to calculate the future state, and then, and this is the crucial part, as well as nudging the middle state vector, you also nudge the future state vector. And as a special case, when this parameter alpha is 1/2, these nudges are equal and opposite, and the 3 time level mean is conserved by that filtering. And it turns out that that is enough to increase the amplitude accuracy by 2 orders. So it propels you from a first order scheme to a third order scheme. So that's some work I did last year that has been followed up here at the Institute. I'll just show you quickly how it works. You do the leapfrog step, and then you do that nudging in equal and opposite directions. So the standard scheme, as it is implemented in contemporary models, would nudge this, but would not nudge this. So this would get nudged, but this would remain fixed. And in my proposed modified scheme, you nudge both the current and the future time steps equally and oppositely. These displacements are of course greatly exaggerated. And because it took me ages to make PowerPoint do that, I'm going to play it again. No, we haven't got time. So here's a simple test integration of this simple harmonic oscillator system with given frequency. I'm plotting the solutions for x and y here, the exact solution, which is of course known analytically to be sines and cosines. The red is what you get if you use the scheme that is used in contemporary climate models, and the green is what you get if you use that modified scheme where you do the two equal and opposite displacements. And you see immediately the well-known dissipation, the spurious numerical dissipation of the Robert-Asselin filter, which is relieved by the proposed modification. This modification is of course trivial to implement in an existing code. So here's some existing code that's imagined to be within a time-stepping loop in your model. Of course you compute the tendency, which is not this easy, if only it were. But anyway, you compute a tendency and then you do your leapfrog step using that tendency to compute the next state from the last state. Then you compute the filter displacement and then you apply the filter. That's what's done in most contemporary weather and climate models, either of the atmosphere or the ocean. To implement the modification that I've talked about, of course, is trivial. You just add this code in red. Instead of adding d to x this, you add d times alpha, and then you perturb x next as well. And the interesting case is when alpha is a half. So instead of adding d to x this, you add half of d, and you subtract half of d from x next. And just by inserting this red code, the amplitude accuracy of your time-stepping scheme gets 2 orders better. The gory proof of that is in this paper. I won't subject you to it today because I don't have time. Right, so just in my final few minutes, just a few implementations of this modified scheme. Here in Cosmo, which is a European, actually it's a numerical weather prediction model, not a climate model in this case. This is just a case study. It's a single 72-hour forecast for, and what's plotted here is accumulated precipitation over those 72 hours, over a certain domain, I forget exactly which, over Europe. And you see that there are various different schemes possible in this model. RK3 is the third order Runge-Kutta, a very sort of well-respected high order time-stepping scheme. And I just make the basic point here that you get more precipitation using the leapfrog with the Robert-Asselin filter than you do with the higher order scheme, which is presumed to be better, more exact. And you can almost match that by implementing this modified scheme. It's become known as the raw filter, by the way, rather than the RA filter. The benefit, of course, is that this RK3 scheme is very computationally expensive and the runtime memory requirements are high. And neither of those problems is suffered by this scheme that's been proposed, and it's almost getting the same precept. That's just a single case study. We can look at a study here which was done by launching 2 48-hour forecasts every day over this period. And what's plotted here is the frequency bias index, which is defined to be the number of times in this period, in these forecasts, for which precept was predicted between 2 to 10 millimeters per 6 hour, divided by the number of times it actually did rain between 2 and 6 millimeters, 2 and 10 millimeters in 6 hours. So it's a frequency bias index. It should be 1 for a perfect model, of course. But it's about 1.4 or 1.5 with the Robert-Asselin filter. So precipitation events in this interval are over forecast in this model, but that bias is again partially relieved by using this modified time-stepping scheme. I want to talk about an implementation in a simple atmospheric general circulation model called SPEEDY. work done with some collaborators from Maryland. And what we have done is to implement the filter, the modified filter, and launch, in this case, 2 integrations which are identical apart from the use of the different filters. Of course, after time, the 2 simulations diverge. What's interesting, though, is if you look over a long period of time, making forecasts with this model and comparing them with observations, and that's what's plotted here. The ACC is the anomaly correlation coefficient, which is a skill score for surface pressure in the tropics based on pattern correlations. And not surprisingly, the further ahead you try to forecast in time, the lower is the skill score. We all know that 1, 2, 3, 4, 5 and 6 day forecasts are not as skillful as 1 and 2 day forecasts. But the key result here is that the skill score is better with the modified filter, the raw filter, than it is with the default Robert-Asselin filter in this scheme. The differences here are statistically significant. And in particular, 5-day forecasts using the raw filter turn out to have about the same skill as 4-day forecasts using the default time-stepping scheme, as you can see by comparing these points. So, just an example there, albeit in a simple model. And the caveat here is that this is a research model, not an operational model. So the background skill scores are not very high. But nevertheless, we see this improvement that comes not from tuning the model parameters or implementing better parameterization schemes, but simply from adding that 1.5 worth of code to improve the time stepping. I'm coming to the end. There's also an implementation in the Hadley Center Ocean model. HADCM3 uses this time stepping scheme, and a bias in sea ice is relieved by upgrading to the modified scheme. But I don't have time to tell you about it. So I've just argued that time stepping is an important contributor to model error, and that the Robert-Asselin filter is widely used, but it's dissipative and it reduces accuracy. I've proposed a modified filter that relieves these problems and is trivial to implement. And in my final few seconds, John, if I may, I just want to put this case study up of a bit of outreach, which has been a part of this workshop with the Willis thing a few weeks ago. I mean, the Sunday Times did this feature article on the future of British science a few weeks ago. And I think there are some lessons to be learned. First, for those who aren't from the UK or don't live in the UK, there's a great example of the first law of British science journalism here, which is that you can't write a science article without calling the scientist a boffin. And that's what happens here in the 1, 2, 3, only the 4th word of a 10-page article, and there's the boffin word. And I was slightly in 2 minds because, yes, we were made to put these white coats on, and I've never put a white coat on in my life. And it was obviously very windy in my part of the lab here, very localised bit of wind. But this poor guy had to hold a raw chicken for half an hour while they took the pictures. So I was in 2 minds about this because of the stereotyping and all of that. But I think one of the good things to come from it was that we each had a profile on the following 10 pages, and I just point out in mine that it's possible to get an entire paragraph in the Sunday Times, a major national newspaper, about the leapfrog scheme in climate models. Time is divided up into discrete chunks. The model makes predictions by leapfrogging from one chunk to the next, and so on and so forth. I just think for those of us who, perhaps worry a bit about communicating the complexities of climate science to the public, if you can get the Sunday Times to write a whole paragraph about the leapfrog scheme, I just think that's immensely encouraging. But finally, at the end of my interview, I was asked where I thought climate science would be 10 years from now, and I said, well, a key priority has to be, of course, to reduce uncertainty in model predictions. And what got written, if you can see, is within 10 years, I think we'll see a model that predicts the weather and climate change exactly. You win some, you lose some. That's it. Thank you.
We have time for some questions. Yes.
Would this have any consequences on the IPCC predictions What is that famous diagram? Do you plan to look? Were any of those computers part of the ones that did?
No, I mean that's the critical question, and I don't know what the answer is. So I suppose you're saying how big is uncertainty due to time stepping compared to the other sources of uncertainty, and I don't know.
Do you plan to look at that?
It's on my to-do list somewhere, but it might be one of those things I never get around to doing.
Gosh, lots of questions going on here. I think I shall have to determine the order and say we'll stop after that. Cecile, Matt, Tim, and Chris. Cecile.
In the GFS, unfortunately, the vorticity is on one side of the leapfrog term, and the divergence is in the next one, and they never see each other until they come together after many time steps to be synchronized. I mean, how... Oh, by the way, I have to tell you, Roger Tamam once told me that he did not believe that anybody would be so stupid as to use a leapfrog scheme for a hydrodynamic problem.
Absolutely, numerical analysts hate it. It's not a good scheme, but
Yeah.
it is
But
what's
anyway,
used.
I showed him an example. But anyway, but the thing is, though, if your vorticity and your divergence never get to talk to each other, how do you implement something like this?
Yeah.
And the reason I'm interested in it is because it was because of that dichotomy that I could not devise a nice, easy stochastic parameterization.
Right.
So if you can show us how to implement this, you're solving more problems than that one.
Yeah, I mean, again, that's future work. The analysis I've done is for just the simple basic leapfrog, which is the same every step and doesn't involve periodic coupling every few steps with some other parts of the model. So I have no answer, I'm afraid, yet for that.
So at any one time point, you effectively have two versions of the variable. Which one do you archive?
Well, that's the case currently with the standard scheme, of course, because you have there's nudging in the current Robert-Asselin filter, so you have two versions of that, and you archive each time you do it, you overwrite the previous, so you archive the filtered version. Although I think which version you archive doesn't matter.
This is not much of a conservation.
I don't know. Certainly, these changes are very small. I mean, the filter parameter is 0.01 or 0.001 typically, so they're very small nudges. I mean, the point is to affect the accuracy without affecting the stability, and I think which particular thing you archive, I think matters less.
I just wondered if this has any relevance to the semi-Lagrangian schemes that are used in most weather forecast models now.
Not yet. Again, that's on my to-do list. The work I've done here has been to look in semi-implicit schemes, where the fast parts of the equations are treated implicitly and the slow parts explicitly. So that's that's this preprint actually, and this paper here. But I haven't yet looked at in a semi-Lagrangian context. Again, it's on my to-do list. I'd like to do it.
Yes.
I was going to make a similar remark, because I was going to remark, if you look in a book on numerical analysis, like, say, Morton and Myers on partial differential equations, because you're trying to solve a partial differential equation, not an ordinary differential equation, and nearly everything you said was about time-stepping schemes for ODEs.
Yes.
Now, we know when we solve a PDE, you should consider a refinement path, not just the time step. You've got to think of in the simplest thing, it would be just the Courant number. It's the ratio of the time step and the spatial discretization that matters. And we know that the accuracy is optimal when the time step is not zero.
Yeah.
That it's better if the Courant number runs near 1 if it's just, say, a straightforward upwinding scheme. And with a semi-Lagrange scheme, the longer the time step, the more accurate it is.
Right.
So the best sort of schemes are to take long time steps of the advection and then micro time steps to do things that all happen in a single grid block.
Yeah, I agree. I mean, I can only say again about the future work that needs to be done. I mean, the examples I showed were, of course, implementations in models with space as well as time in them. So it does seem to work empirically in the models, but the theoretical analysis that would underpin that, I think, remains to be done.
And I thought perhaps, given what you just said and the links with the parameterizations, that it actually would be a very interesting experiment to treat the time step as a parameter and get the data assimilation system to work out the probability density for it.
Yeah.
Well, David's obviously burning to ask a question here. I think otherwise, or you might be a popular dining companion tonight.
I hope so.
David.
So my experience of numerical schemes is always a principle of misery, right? So you've increased accuracy. Do you lose something on stability at all? Is the domain of stability, is it less stable in certain conditions than the old inaccurate Robert Asselin?
So
Sounds sceptical.
it is, and that's why the best value of alpha is not actually a half, but slightly greater than a half, 0.5001 or something. So if you use alpha as exactly a half, there's a very weak instability, but you can recover a finite stable range by making alpha a half plus epsilon, and the value of epsilon allows you to tune the extent of that stable range. Yeah.
Not as stable.
But the implementations I've shown have used actually alpha equals a half, which is technically weakly unstable, and the model still runs because physical damping in the model, or numerical damping from other sources, turns out to be enough to control it.
So have you Lorenzo tractor as well?
Sorry, I haven't looked at it yet. Yeah.
The whole back in it.
Yeah.
Good. Thank you very much. Come back.